is Leslie Lamport, and I am a computer scientist, which is something that didn't really exist when I started being a computer scientist, and it took me a while to figure out that I was one. My relationship with computers began as a programmer. It never quite occurred to me that I was doing anything scientific until after I had published enough papers that it finally occurred to me. My education was as a mathematician. It was just natural for me to think about computers as a mathematician. When you write an algorithm, you need to have a proof that it's correct. An algorithm without a proof is a conjecture. It's not a theorem. And if you're proving things, well, that means mathematics. Computer scientists tend to think in terms of programming languages. One of the epiphanies in my career was the realization that I was not writing programs as a computer scientist, I was designing algorithms. I came to realize that if I'm not writing a program, I shouldn't use a programming language. People confuse programming with coding. Coding is to programming what typing is to writing. Writing is something that involves mental effort. You're thinking about what you're going to say. The words have some importance, but in some sense, even they are secondary to the ideas. In the same way, programs are built on ideas. They have to do something, and what they're supposed to do, is like what writing is supposed to convey. If people are trying to learn programming by being taught to code, well, they're being taught writing by being taught how to type, and that doesn't make much sense. The best way I have for teaching about programming, as distinct from coding, is to think about what the program is supposed to do mathematically. There's a very big practical problem with this. The mathematical education in this country is pretty terrible. Most people wind up being afraid of mathematics. This is even senior programmers. I've developed a language called TLA Plus for writing down the ideas that go into the program before you do any coding. It's a pretty hard thing for engineers to get into, but when they do, it develops their ability to think mathematically. A distributed system is one in which your computer can be rendered useless by the failure of a computer that you didn't even know existed. Non-distributed computing is when different processes communicate by using the same memory. And distributed computing means that they're communicating with one another by sending messages. Now, my interest in distributed systems came about by serendipity. I received a preprint of a paper by Robert Thomas and Paul Johnson, who had an algorithm for implementing distributed databases. These are databases where you could have multiple copies of the data sitting at different computers, so that programs on each computer could have rapid access to the data, but they had to be synchronized so that processes on all the computers got consistent views of what the data was. I happen to have become quite familiar with special relativity. One of the things that special relativity teaches you is that two different observers can have different notions of what at the same time means. But there's one notion that is invariant. There's a certain notion of one event happening before another event. And that means that it's possible for information to be transmitted from one event to the other when the information cannot travel faster than the speed of light. I realized that that notion of causality was violated by the algorithm of Thomas and Johnson. It's completely analogous to the relation in special relativity. So what I did is I wrote a paper that explained this notion of causality. One could solve any distributed system problem by building what I called a state machine. Think of it as an abstract computer that does one thing at a time. You make sure that all the computers in this distributed system cooperate to implement a single state machine. And that idea has become fundamental in the way people think about building distributed systems. I had never even thought about a distributed system before I wrote that paper. As I progressed in my career, I came to appreciate the idea of working in industry. That's where most of the interesting problems that I found came from engineers having a problem to solve. It reminds me actually of something that Auguste Renoir once said. Someone asked him why he painted outside rather than in his studio. And what he said is, if I were painting in the studio and I wanted to paint a leaf, I would be able to think of only a half dozen or so different kinds of leaves that I could paint. But when I was painting outdoors, there were just these millions of different kinds of leaves that were there that I could paint from. I found my research the same way, that if I sat down, and just, contemplated my navel and think about problems, there was this small number of problems that I could think of. But there were just scads of them sitting out in industry waiting to be solved. My favorite of my algorithms is the bakery algorithm. It's to solve the exclusion problem, that is, keep two processes from using the printer at the same time. Processes choose a number based on the numbers that have been chosen by other processes and use an algorithm so that the lowest is allowed to use the printer. But what is amazing about it is it does not make an assumption that almost every other algorithm makes. The assumption being that if, say, I'm changing my number from 47 to 100, and you read that number, you'll either get 47 or 100. But that algorithm works even if instead of getting 47 or 100, you maybe got 4,700, or maybe you got 9,999. The algorithm still works. I didn't intend it to. I didn't intend that. I just discovered that when I wrote the proof, I never needed to make the assumption. That is just so beautiful. And I'm really proud that, that I stumbled on it.
That's nice. Yeah, I wasn't really familiar with Leslie Lamport, but that was a good video. So, what's up on the dock today? We were working on this stuff last night, some of these bit flipping things. I was able to solve a few. Why is this owned by root? The labs directory is owned by root? Maybe because I ran the container and it owned it, maybe? What's going on there? Okay, so that's the repo labs. And then there's a labs directory inside here, tree labs, or I should say LT labs. Such RMDR labs. Okay, that was just like a junk thing. Git status, vim, bits. Alright, so I was able to make some progress on these. They're not easy. Some of them are easy. One of them is. So the bitwise XOR, this one was stumping me. You only allow these two operations, and you can only use certain numerical constants. And you need to implement XOR. So my initial attempt was to just ampersand and then negate one of the operands. That didn't work. So I kind of went through and I created this truth table of different expressions to try to explore the possibility of like what can I do to make it to where I can get this bit pattern in the output. And so in doing that, I discovered, I can select for this one bit here with X and AND. I can select for this one bit here for with not X and not Y. Sorry, X and Y not x and not y. And then I created this expression here, which selects for nothing. So I can select for everything because I can negate it. So that's pretty much what I did is I selected for nothing and then I negated it, which is a negation of 0. So all bits are 1. And then I ANDed that with the negation of those two expressions. And that gave me the correct result. And it did it in less than 14 operations, which was the goal. Looking at this, this doesn't really seem to be obviously to be the most simple thing. Like perhaps there's opportunity to simplify this even further. Like some things that I noticed is that the negation here is being distributed. Perhaps I could avoid doing that somehow, but the only way I know how to do that is De Morgan's. And that involves flipping the and into an or. So yeah, I'm not gonna be able to do that because I can't use the or operator. Anyways, so that was that. This next one was really easy. T-min, you just bit shift over 31 bits. Knowing that int is a 32-bit integer, you just bit shift over 31 places. And that's allowed because the bit shift operator is allowed there. This worked, but basically, so the goal of this is to find T max, which is a 2's complement maximum, which has the pattern that we see up here, where we have all 1s except for the most significant bit is a 0. That is the maximum value that you can have in a 2's complement 8-bit representation. So what did I do? Well, you can just say, we'll take all the bits. Sorry, we'll take that bit pattern here, and then we XOR that with X, and then we negate it. And you can see that here. So this is the original bit pattern. If we XOR it with this, we get out 0. And then we negate it to get a 1. If we XOR that with some other arbitrary pattern, we get this thing, and it gives us positive, and we negate it to 0. So this works, but relies on us having this very large constant. And we're not allowed to have those. We're only allowed to represent between 0 and 255. And then I could also represent -1 by negating 0. And so I was thinking about this off stream. So Tmax returns 1 if X is the maximum, 2's complement number, and 0 otherwise. The legal operations are not the negation of all bits, ampersand XOR, or plus. And we have 10 operations to do that. And so I was just like, how do I do this? How do I do this? And I haven't figured it out off stream. So I'm going to work on that now. And hopefully some of the techniques that I discover in doing this propagate into the next problems, because I looked ahead a little bit and those aren't easy either. So my original strategy was to get a bit mask that matches the value that I'm wanting to match against. And I think that's a really good strategy, but the problem is that I have no way of getting that bit mask. So say we try it with addition. So we have one input, which is X. If we XOR it with ourselves, then we get all 0s. If we XOR it with our inverse, then we get all 1s. In both cases, we can get that value by other means, like 0 and -1, which is all 1s. Both of those values we can obtain by other means. So I'm thinking plus might be needed here. The property that I was thinking of is when you overflow. So we can add 1 to a value and negate it, then it needs to be its negative. That is a property that I observed earlier in the day. Just thinking about this, is that if you have a 2's complement 32-bit number, any 2's complement number, if you negate its bits and add 1, that would negate the value. And where that doesn't work is when the value is T-min. So that's a way of detecting T-min. That's not a way of detecting T-max. Unless you add 1. You can add 1, and then you can detect T-min, because 1 would overflow. So let's just type that out. I doubt it's going to work, but... So if we do something like x plus 1, now we would have overflowed. And then... I'm going to say, is this value, if it's positive, if it's 0 or positive, in fact, if it's any number, if it's greater than x, basically that's what we want to implement. But we can't use this greater than sign. So there's a way of implementing greater than using these operators. Okay, let's think about it. What does it mean to be greater than another number? Well, we could say 3 is greater than 1 because when you AND them together, you get 0, 1? No. Well, you get 0, 1. Actually, let's do here, and we'll do two cases. This case, there's actually 3 cases. So the first case is 1 0 with 1, 1 0 with 1 0, in which case they're equal, and 1 0 with 1 1. So these are 3 cases, and we want to find a binary, bitwise binary operator that, when applied to these numbers, tells us that it's greater than. So it'd be this first case. So let's try AND. I'm just going to do like a table here. So I'll have AND here. So ANDing these two together would be 0, 0. And this would be 1 0. And this would be 1 0. So this should be less than, equal, and greater than. I'm going to comment these out here. If we can implement this without greater than, then we have it. I'm gonna pull this out here. Okay, I think we have it with an AND, right? Because well, let's do a 3-bit. Let's try it with 3 bits first before we claim victory here. So this is clearly greater than this. This is clearly greater than this. And these are clearly equal. So here we're going to say and is going to be 0, 0, 0. This one, I think we need to set some different values here too. 0, 1, 0. This would be 0, 1, 0. But is there a value that's greater that is a different bit pattern? Like I'm thinking this 0, 0. Yeah, when you and this together, this is clearly greater than this, but you and it together, it just happens to come out 0, 0, 0. So this is ampersand is not the solution here. Because I didn't have exhaustive coverage on this. Alright, let's move on. So ampersand is not going to work. What about XOR? We're allowed XOR. So XOR would be 0, 1, 1. XOR here would be 0, 0, 0. There was something I was thinking of earlier. But I don't think that'll work. This one would be 1, 1, 0. And this one would be 1, 0, 1. So XOR is kind of nice in that if you XOR it with itself, then you get 0. Like any value, if you XOR it with itself, it's going to come out with 0. So you can tell if it's equal to itself, but you can't tell if it's greater than. And so what I was thinking before the other day is that what if we did something like was equal to x minus 1? What if we did that? But that won't work because x plus 1 will overflow. So this will overflow to tmin. And then we say x wait a minute, minus 1. And if you subtract 1 from tmin, I think you go back to tmax. Okay, sorry, I'm thinking here. So tmin has a property in that it is its own negative. And we know how to get a negative of a value. I think that might be it. So what we need to do is, take x plus 1. And now we need to take x plus 1, negate its bits, and then add 1. And then XOR them together. And if that is that should equal to 0. I think this might work. Let me just run the test on it since there's a test suite already available here. I mean, there might be precedence issues here. I think maybe we wrap this just to be safe. So what we're saying is x plus 1, there's two situations here. Either we overflow into tmin, or we just go to the next value. In which case, if we do that and then we negate all of our bits and add 1 to it, we should have the negative of the value, which will not XOR to 0. So this is going to XOR to 0. If we look back at our initial problem statement, we need to then negate this whole thing, which just be a not sign here. Sorry, a not sign. I think that might work. Make btest. Which one is this? This was no. Is tmax? I thought I might have had it there. Maybe we need double negation. I'm just gonna try this because we have test suite. Sorry, make. No. Okay, back to the drawing board here. Okay, so I think I had something here though. Let me pop open Clang REPL here, if I can. Clang REPL include, and I want to just test this out on a unsigned. Let's do standard int here. And printf percent the new line. Actually, yeah. And then I'm gonna call is tmax on, say, 0, and that defined is tmax, and I'll define it as this. I need to rewrite this to be a int 8. We'll call it a int 8. I think t. Yeah. int 8t. Just to limit the amount of bits that we're dealing with here. Let me paste that in there. Okay. So now I can go up here. 0, 1. If I do like 0x ff, which is -1. This will be -1 here. Interesting. Okay, so this is all over the map. Is our precedence getting messed up here? Yeah. It needs to be negate x plus 1. No, that was right. Well, let's break this out into multiple lines here. Let's try implementing this a little bit differently, where we have int 8 t, we'll call this y, which is going to be x plus 1. And then here we take y and y here. So what's going on here? Well, x plus 1 in every case, whether you're absolute T min or you're all the way up to every value except for T max, when you add 1, that value is going to be different. It's going to be a different value, numerical value, and also obviously a different bit pattern than where you came from. I think that property, okay, so what makes T-min unique is that if you negate all of its bits and add 1, it gives you the same value. Whereas everything else, if you negate the bits and add 1, it gives you a different value. It gives you its inverse. It's negation. So what we want to do is we want to have the ability to test for, is this T-min? So if we go back up here, we did that with bit shifting up there. So the way that we tell if it's T-min or not is we say, okay, well, we're going to say, do you have the same bits as your negation? So we're going to negate all the bits, and then we're going to add 1. I'll put precedence around this, or sorry, parentheses around this to force the precedence. So this should give its numerical negative. In which case this should come out as 0 if it's T-min, or anything else it should not come out as 0. So let's test that assertion. Can I redefine? Redefinition of is T-max, okay. We'll just put like a 2 here. So it can't redefine. Oh, never mind. Okay, we'll do standard int. And then, okay, I'm not gonna mess around with that because I just want, sorry. I'm just gonna call this thing test. And I need to go back here to labs. Data. Just call it test.c. Pound include standard io.h. And then I'm going to copy over my implementation here. Paste that bad boy in there. Copy this thing over. Do standard int. Okay. And now in our main, I'm going to go over, need standard lib as well. Okay, in our main, I'm going to say, hey, for int, sorry, not int 8t, I is equal to, so this is a single bit, 0x, what is this going to be, 8, 0? I is less than force this to be int 8t. I is less than the maximum value, which will be 7x f. But we can say less than or equal to. Then we do I plus plus. No, we can't do that though because it's gonna wrap around. So I can't do this because it's gonna go from Tmin to Tmax, and it's gonna overflow. The plus plus is gonna overflow. But say this worked, then I'll just do, just to get this thing out, printf out. What do I want? %d here, and we'll just do it as a function call and say is Tmax. We call it is Tmax. We don't need to have the 2 there. And that results in %d here as well. And we give it I and is Tmax of I. And we'll just say here, we'll do standard bool. And we'll say bool is first iteration. So equal to true. If not is first iteration, and what would this be? I is equal to this value. Then we just break. And then we need to say is first iteration is false. Okay. Make. Okay, that didn't work. What do I want to do here? GCC test.co test. So -1 gave us a 0 point. 127 gave us a 0 point as well. I didn't expect that. It's working mostly, except for these little edge cases around -1 is an edge case. We'll have to look into that one. But you can see it did detect Tmax. So why is -1 failing on this? Let's walk through it. So we got -1 plus 1. Oh, because it's 0. Damn it. Because the negation of 0 is going to be 0. Forgot about that. It gets you almost there. The negation of 0 is also 0. That's the problem that we're running into there. So Tmin does share the property where its negation is itself. It shares that with the 0 point. Is there something that's unique about 0 that we can exploit? So close. It's just one value off. And I think I can remove this from the test code here. So I'm pretty sure that'll be, yeah. Yeah, same thing there. Damn, it's so close, man. It's freaking -1. So we have other operators that we can use. And or XOR. I think we probably got all the mileage out of the negation, not in plus, that we need. We might need to exploit one of these other operators to like handle the case where 0 is what we need to do is we need to have an expression that's effectively a no-op, but when the value is 0, it emits a bit in any place other than the leftmost place, because then we're back into tmin. So I'm trying to think of an operation that might do that for us. It is not jumping out to me though. I imagine most of these college kids are just like ChatGPT and this stuff these days, but I want to like actually solve this on my own. So I think that the truth tables have been a helpful tool. And just sitting back and like thinking about it. I mean, practically, this stuff is a lot easier to solve when you can just have like larger constants. The constraints on this problem are a bit unrealistic. Because like in C, you could just create whatever masks you want, and like you don't have these artificial constraints. Let me fix this up a little bit here. Well, I guess and is an important property. Where if you and 0 with anything, you get out 0. I don't know if that's going to help. Well, let's do a 2-bit example here. So we're going to have 0, 0, 0, 1, 1, 0, 1, 1. And we want this to go to something that's other than these two, or these three, sorry. So if we That's a bummer. I can't think of anything. That was a second promising route that I'm going to have to abandon here because I can't think of how to eliminate the 0 case. Because as soon as you eliminate the 0 case, you're also going to eliminate T-min. Because T-min goes to 0 as a result of the function. So you have to eliminate 0 before. Basically, you got to get 0. If you could do like an if it's equal to 0 plus 1 before you go into the rest of this, that would work. Oh, it's so close, man. It's frustrating. I'll add another note here. God, I hate this thing. I was so close twice now. Maybe we go back to this approach. X plus 1 being greater than. Because that would be the case. I think I need to do that. Let's go back to this solution. Because again, if I can implement that, let me actually just do that here. I just throw a not in front here. Make zero. Maybe it's a negation. Maybe I messed that up. Let's make sure that we have precedence correct here, just in case. Huh? How is that not the case? Oh, because this is because we're dealing with we need to go to what? In 8T. So 127. I think it's 126, right? No, 127. 128. $127. If we do +1 to that, it would loop around. It would be negative 128. Which case that should fail. Oh, that's confusing as fuck. Okay. Yeah, what's 128? Shouldn't do that. It should loop around. Because it's at int 8t. If I go to definition on this, it's assigned char. I is an int 8t. How do you go to 128? That's not a valid value. I don't like this. How do you get to 128? If we go back over to here to 2's complement calculator, and we say that we have a 8-bit, I want to enter, it goes from it goes to 127. You can't have 128. 128 is not a 8-bit representation. Maybe because it's %d. That's probably why it gets up converted in the printf. Okay, I'm going to ask AI something not related to answering the question, but just something separate. Is an int 8t, or sorry, I should say, does t in C wrap around if you go past 127? It's going to be no. Signed integer overflow in C is undefined behavior. That worked. So something about my addition is jacked up. Oh, it needs to be like this. Okay, great. Yay, there we go. So one thing we need to do here is just make sure that we do our comparisons with the date. So this works. This passed the test. So if I go back over to here, the only thing I have to do here is say, hey, x plus 1, you just got to make sure that you're a int. Okay. And then if we go over here and make btest. Okay, so it works seemingly for everything except for the value that we want, which is perplexing to me. So x is an int. Just ask AI here. Define behavior. Huh. Yeah, dumbass. Oh, I have this and instead of bitwise and. That's probably it. All right, go away. All right, I'm just gonna hop off here and take a break because this has hurt my brain, and I don't want to rely on AI to solve these. So I'm gonna take a break, get some food, and I'll be back on a little bit here to continue working on it.